Good afternoon, guys. Today we're going to discuss kinetic molecular theory and its implications, if you will, on gases. Part of this conversation is very theoretical. Actually, the majority of it will be very theoretical. The rest of it is, there's just a little bit of math, and after coming out of the stoichiometry unit, that math is going to seem so easy that I don't really spend a lot of time on it in the video. If after we practice it in class, you're still a little confused, make sure you mention it, and I'll be sure to spend more time. So, kinetic molecular theory. You'll hear me refer to it a lot as KMT, but it is often referred to as kinetic molecular theory, like in your book. Kinetic molecular theory basically talks about kinetics, which is movement, and molecular, which is molecules. So we're talking about how molecules move, or actually more importantly, why they move the way they do. Now, there are some basic theoretical constraints to KMT. All theories have some prior knowledge that they're based on. I don't want you to think that this is a theory and so it doesn't really matter, because theories are pretty much the entire basis of chemistry. There's no way we can shrink ourselves down to the size of an atom, and so everything that we have is from inference and not from direct observation. So, but there are some presumptions that they make in order to explain the concept. So, the first thing is that we're talking about atoms that are super duper 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 small. Okay, one of the challenges with this particular unit, and I've talked about this before, is that a lot of the images blend the submicroscopic and the macroscopic at the same time. So you can see the water molecules drawn in a glass, or the atoms of helium drawn in a balloon. But the fact of the matter is, if you were shrunk to the size that you could actually see the atom, there's no way you would see the balloon. It would just be too big. It's kind of like seeing the surface, the outside of the earth, if you will. The earth's outside is so big, we don't actually see it even being on earth. So the particles are very, very small. Next presumption is, when I say the particles are very small, they're also extremely small relative to their container. So the size of one human relative to the earth is really, really small. So we really don't even consider the weight of people when we're talking about it. When we're talking about atoms, the size of the atom is irrelevant compared to the container. One way I describe this is if I think a room is mostly dirt, or if I think of a classroom, take my classroom for this instance, and I have someone sweep up all of the dust that's on the floor, all the dirt that's on the floor. The pile is actually very small compared to the volume of the entire room. So I would never say that the dirt on the floor in my classroom prevents me from putting out desks or prevents me from having students, because the size of the dust is small compared to the volume of the entire room. Likewise, the size of the atom is small, almost insignificant compared to the size of the entire container. The next thing is particle motion. Motion meaning that particles, we're assuming that when particles move in this theory, they move in a very straight line, an absolute straight line. So not like a bullet in an arc, but they move in a straight line. Not only do they move to a straight line, but all collisions are elastic. That means when they hit something, no energy is transferred and everything is just kept within. It's conserved within the atom, and the atom bounces back with the exact same amount of force as it hit the side of the container. Think of it like one of those super balls that you got when you were a kid, like from the supermarket, and you would bounce the ball. I think sometimes you get them from like Chuck E. Cheese. Anyway, you bounce the ball really, really hard and it bounces up super duper high. But those collisions aren't elastic, because if we watch them slowly, every time the ball bounces back up, it bounces a little bit lower and a little bit lower to the point that it actually eventually will stop bouncing. That is an inelastic collision. Those are the collisions that we see that go on in the world. However, theoretically, you also could have elastic collisions in which no energy is transferred. Nothing went from kinetic to potential energy. It all stays as kinetic energy. Particle energy. Since we're talking about particle energy, we are talking about specifically kinetic energy, because this is the kinetic molecular theory, and we're talking about the motion of molecules. So the energy is primarily as kinetic energy, though there is potential energy. Potential energy is usually stored in the form of bonds. But in terms of the kinetic energy that's of the atom, we measure that by measuring temperature. Temperature does not measure heat, never has, doesn't measure heat. I know you're confused because when we look at the weather report, it says that it measures heat, or we're figuring out how hot the day is. But that's because we're ignoring a lot of other factors. In a scientific context, temperature is the measure of average kinetic energy. That's the definition that you need to know. Temperature is a measure of average kinetic energy. Average kinetic energy. Think of that kind of like a classroom in terms of, or school. If I say a school is average, that doesn't mean that everyone in the school actually gets the same average C grade. There are going to be some people who are getting, 1800s plus on their SATs, and those people are going to be at the upper end. And then there's going to be some people who just never come to school and they never do any work, and so they're going to get a 0%. The average is literally the mean of all those people in the middle. So when we talk about the fact that a room is 95 degrees Celsius, well, truth be told, we don't really use Celsius in kinetic conversations. We usually talk about Kelvin, and we'll talk about that equation later, but you probably should know it. K is equal to C plus 273. We talked about it way back in chapter 3. So when we talk about kinetic energy, what we're really talking about, when we talk about temperature, we're really talking about an average of how fast the molecules are moving in a particular space. So the reason that my room feels cold is not that there's an absence of heat. Heat is energy and it's not matter. So technically, it's not that it doesn't exist, but it can't ever be touched. However, kinetic energy, on the other hand, is something that's actually measurable. And kinetic energy, actually, to be truthful, heat is also measured, but we talk about that in physics. Sorry to go on a sidebar, but kinetic energy is something we measure through the use of temperature, and it measures how fast the molecules are moving. The average of how fast the molecules are moving. So what makes gases so special? Why do we focus on gases? Well, gases are kind of like the ideal. They're like the best case scenario. So gases, you have only a few molecules in a single container in a balloon. That's why most gases are transparent or clear or see-through. They're very hard to see because the density of them is very low. They are actually, to be honest, we never actually see a gas. We see other things condensing on a gas. So even when we're looking at fog, we actually aren't seeing gas vapor. When we're looking at fog, we're seeing the water droplets condense on the gas vapor. So gases are so low density that we can't really see them by themselves. They're compressible and expandable. Because they're so small compared to their container, we can actually smush them in on themselves, and because there's plenty of room, or we can let them spread really, really, really far out. Think back to our conversations at the beginning of the year about the cookout versus the group of Marines versus the gases, and how the gases were so far apart that they didn't even know that each other existed. Diffusion and effusion. We'll talk about effusion a little bit later, but diffusion, we know this very well. Someone comes in wearing good cologne and we smell it throughout the room, or worse, somebody passes gas in one part of the room and we smell it in another part of the room. That process is called diffusion. You've learned about it in biology class in terms of diffusion and osmosis. So you're familiar with osmosis happening in water. Diffusion happens in everything. Osmosis is a special kind of diffusion. But what I also want to make a point of is effusion. Effusion looks at the speed of those molecules. We'll talk about that later in terms of Graham's law. But basically it happens that really small molecules move faster than really big molecules at the same temperature. Don't worry about that. I'm just introducing that concept. We'll talk more about it in 13.4, I believe. Where we're talking about gases, liquids, they are different because some of these things are not as true. They're not as compressible. They're not very expandable at all. There is diffusion and effusion, but it tends to happen slower. And also, they're higher in density. Solids are almost not at all compressible, definitely not expandable. That's why things break when you heat them up, because they don't expand with heat. The diffusion and effusion could potentially happen, but we're talking about over centuries, and they're very high density. So when we're talking about kinetic molecular theory, a lot of it focuses on gases because gases are so far apart that their interactions don't affect each other. whereas the interactions of, say, two liquids do affect each other because they're attracted to each other. A good analogy to that is, how someone acts in the hallway makes a difference, because if that's your boyfriend, because now you have to respond to how he's responding, or vice versa. You have to respond to how she's responding. We have to respond to how other people respond to them. So likewise, liquids and solids, they are kind of linked all together, kind of like in a relationship. And so even though they're independent molecules, they're kind of connected, and so they can't really get rid of each other as easily. So the last part of this video is a practice problem. And before I get into the practice problem, I want to talk about pressure. Pressure is the result of particles pushing outward. So if you have a really bad headache, what you're usually feeling, especially around this time of year, is sinus pressure, the pressure of the molecules in your sinus pressing outwards on your skull and the blood vessels in your brain. So there are a couple different measurements of pressure. There's atmospheres, millimeters of mercury and torr, which are the same thing, and kilopascals. Now I'm going to go ahead and stop the video now, and we're going to, you can look at a second video. We'll call that video 11.5 if you want to see how to do the pressure conversions.